Morning, everyone, and welcome to the 8th lecture in robot dynamics. Today we're going to discuss about elect robots. Before diving into the details of this current lecture, let me quickly give an outlook for tomorrow, for the midterm that you have tomorrow. There were a couple of questions in Piazza, and I tried to address them here all together. So the first one was mainly related to the content. What we are discussing tomorrow in the midterm is dynamics. Of course, you need kinematics also for that part, but the primary focus is on dynamics, and we will have an exercise with a fixed-based system, so there will be no floating-based systems tested tomorrow in the midterm. Due to the corona situation, we can't do the midterm here at ETH, so we have to do it from home. It's going to be exactly the same way as you used to have it in the first midterm. We're going to upload the questions on Piazza. You can download them at 8:15. You can do them, the exercises or the midterm question for yourself, and then upload the solution before 10:30. Important is that you have to attend the exam over Zoom. So we are posting a Zoom link on Piazza. You have the link there. Make sure that you log in this main room with your video turned on during the entire exam. That helps us to check on who is there and that you're doing the exam for yourself. Important is that you are signed in with your ETH Zoom account. So that is for us important to check like who attended, that we can see from your name a unique identifier of the person behind. So use your ETH Zoom account. If you don't have yet an ETH Zoom account, make sure that you register under this address that we are providing here. If there is things that are unclear that you have to ask about as you would do during the exam, make sure that you use the Zoom chat. So here are the details. They're also posted online on Piazza with the Zoom link, meeting ID and password. And I mean, a standard procedure, make sure that you're logged in with the proper account. All of that should be straightforward. The same rule apply as if you do the midterm here at ETH, which means you're going to work with your laptop, you use MATLAB, you have to upload everything. The exam will be open book, so you can use whatever you want to use. You can have your PDF open with the theory part, you can have your slides, you can have your handwritten notes, whatever you like. The only thing you're not allowed to is use the internet to get additional information during the exam, except for the license. That's the only thing. Plus, if you need to check for syntax of MATLAB or something. And also important, no communication among the individual people. We will have some checks integrated in the exam, so we'll figure out if people copy stuff from others. So this is it for the midterm. I hope everything is clear. Again, this midterm is only optional. You don't have to attend. It will only improve your grades, or has only the potential to improve your grades, but if you can't attend, no problem at all. Are there any questions related to that? All right. Then we're going to move on with some questions that were raised on Piazza. There were a number of questions. I think most of them are pretty well addressed with the answers that you find there, so don't have to iterate over this again. There's, however, one topic which keeps popping up, and I would like to check this one more time with you, like go through everything to make sure that you understand this well. So last time I make a recap about this support null space projection. I showed you exactly how you can derive this, starting from the equation of motion for a floating base system plus the contact constraints, how we can then insert these constraints and we end up with a projected dynamics equations of motion, which is independent now of this contact force. And I showed you how you can do this. Now, somehow we did this insertion here and we ended up with an equation which had this NC, which is a null space projector, popping up, naturally evolving from the way how we inserted these equations of motion. So I would like these constraints on the contact point. I would like to rediscuss this from a slightly different angle today to hopefully clarify this a little more. So let's make a step back. What we looked at last time was how can we do inverse dynamics control for floating-based systems, so systems that are not attached to the environment. If you look at inverse dynamics control in general for fixed-based systems, what you had was a model description. So we had acceleration part and the rest equals to the torque. And if we formulated these model descriptions of how the dynamics is evolving based on actuator input into a control law, it just changed the order kind of. We got a pre-planned desired acceleration, which is typically a function of multiple objectives that we have in how the system should be moving. We insert this in here. We have the modeled M, B, and G. So if you look at the way how we wrote it in some of the notes, we had here a HUT. So this was the estimate of M, and this gave us a desired torque. Now that's straightforward. As long as we have a good model, we can immediately convert a desired motion, a Q double dot star, into joint torques that I have to apply to the robot. Now, if you look at a floating-based system, the thing is a bit different. For the floating-based system, we had an equations of motion which looked the following way. There's two things which changed. First one is that all of a sudden we had these constrained forces in there, which come in due to the fact that we have contact with the environment, which imposes kinematic constraint and constraint forces on the dynamics. Plus, we had this S matrix here, which indicated that not all degrees of freedom, not all generalized coordinates are actuated. So if I want to figure out now what is my desired torque, similar to this equation up here, what is my desired torque that I have to apply to my system based on a desired motion, I have the problem that there is here some constrained forces that I first have to figure out before I can actually solve the problem. So it's kind of a chicken and egg problem. So what we were doing is we wanted to transform this into another form such that we can do something similar to what we have up here. And the reason is, or the reasoning behind this is, the number of constraints that are typically acting on our system, which are also equivalent to the numbers of forces that we are kind of injecting into our system, the independent force directions that we have. This is lower than the generalized coordinates, so the number of degrees of freedom how the system can move. So what you want to do is you want to reduce dimensionality of this equation into a subspace where this part drops out. Then you have only a part which is motion and a part which is torque. And this is what we are doing. So there's two things which are special here, as I said, constrained forces. And the second thing which is special is while here, I can arbitrarily select my Q double dot. There's no other constraints. Here, my Q double dot has to be consistent with the contacts. So in other words, I have a contact constraint which limits my Q double dot star to be consistent with this constraint. So it is essentially something which is projected into this kinematic null space of the contact constraint. So it can't freely select Q double dot, but we can only select Q double dot such that it is compliant with this constraint. So in other words, what we would like to do is we want to take this equation with a Q double dot that is consistent with the constraint, and we want to project this into a lower dimensionality such that we get rid of the contact forces. So we project the left part of the equation, this part, and the right one, and we have a lower dimensionality here, but independent of the force. This is all we want to achieve. If I have this equation, now I can do the same as up here, where I did inverse dynamics by just changing, bringing the other thing to the left-hand side and vice versa. So here we have to take the pseudo inversion of this P as transposed, the pseudo inversion times the left-hand side. And as we mentioned last time, this is not the only solution. So there is again here, kind of a null space solution, which allows us through our tau zero to change the torque without actually changing the motion of the system. So don't be afraid now about these new P's that are popping up. We'll come to that in a second. What is important here in this one also is to see that, as I said, whenever there's a pseudo inversion, we typically don't have only one solution. There's multiple solutions because it's an optimization that is happening underneath. So we write usually this null space projector here with identity minus pseudo inversion of it minus times the PS one. What you do in reality is you have a numerical toolbox that does this null space calculation for you in a more elegant way, numerically more stable way. So we're writing things up here analytically, but once it comes to evaluation of all of that, we have to resort to numerical evaluations. The very small 1 or 2 degree of freedom examples that we were doing here by hand, these are really the only thing that you can do analytically. Whenever it's getting more complex, you have to do this numerically. The same for this. So these null spaces are typically calculated numerically. Now, what you were doing in the last slide, so if you look at this equation here, if you look back to the last slide, this one, we actually did nothing else than calculating this P by inserting the constraints, calculating the force, back substituting, and we ended in a projector matrix which corresponds to this NC transposed. And this NC transposed was given by this one. So no magic, it was only substituting the constraints and the equations of motion. So in other words, the dynamically consistent null space projector, which is one possible null space projector, is this one. We know that one works. Now, I want to show you a little more of what is possible in here. This is beyond what I expect you from understanding in this class, but I think it can still help you in getting a better grasp on this. Another way of analyzing this is that we are analyzing this JC transposed. So this constraint, this Jacobian that describes the constraint. And as I said, this Jacobian only constrains a subspace of the whole system, how it can move. What we can do is we can do a QR decomposition of this JC transposed. If you want to look up the theory behind that, you can do QR decomposition, which gives you a Q matrix, which is orthogonal, so Q transpose equal to Q minus 1, and it has a block diagonal R matrix and a 0 matrix in here. So this you can do with all matrices. And if you substitute this now in here, so if you take this J and put it in here, I have a R transposed 0 times my Q from here. So I multiply it with Q minus 1 from the left, the whole matrix, which is my Q transposed. So I get this equation here. This is no magic. All I do is I take this, I insert it in there. So I take this thing, I insert it here, and I multiply to this left-hand side a Q transposed to get rid of that Q. So I end up with this equation. The reason I'm showing this is because what you see now is you have a upper part and a lower part of the force. So you can split now the equation into two sub-equations. One sub-equation here, which is independent of the contact forces, and one which has this R block diagonal matrix for F, which is invertible, such that you can directly calculate the force. So this is now a splitting of this whole dynamics of a floating-based system in contact into two subcomponents. One subcomponent here, where I can directly relate motion to torques, and one subcomponent that, given then the torque and the motion, I can directly calculate the force. And if you remember what I showed you last time, and that's the reason I show this here again, this is similar to how we analyzed the whole equations of motion. So we said like we can split. We have also this selection matrix here, which essentially has zeros, produces zeros for all the base degrees of freedom. So there's no actuation at the base and there's only actuation in the joints. So we can separate this into two equations as we do it here. One which is only, the upper one which is only depending on forces and on motion, and the lower one which is depending on motion, forces, and torques. So this is separate splitting of equations. So in other words, all we were doing here with these projectors is reducing from a problem which is depending on Q double dot or U dot, force and torque, to only have two of them in there, such that they can directly relate the desired motion to the torque or the desired motion to the force. But it's only a rearrangement, so I'm solving the problem in one subspace first and then going to the second subspace. So I hope this clarifies it a little more. I have afterwards a couple of additional readings for you if you're interested. All this QR decomposition, SVD decomposition, whatever this goes beyond of what I expect you to do in this class. Nonetheless, I think this is a very interesting topic, and if you understand it better, I think this helps you also in understanding the whole thing. So let me go here through a couple of questions. The last one was, if we apply this dynamically consistent null space, can we then have an arbitrary acceleration? So what is important here is this acceleration that I'm choosing here, this Q double dot star, this always needs to be consistent with the constraint. In other words, I cannot arbitrarily choose it, because otherwise I produce a desired motion which cannot be achieved. So I have to first, if I have an arbitrary motion, I have to first project it into the support, the kinematic null space, which is this thing up here. So I pre-multiply a generic Q double dot zero with a projection matrix to ensure the constraint is satisfied with my Q double dot star, and then I put it in here. Now what I have here is the identity minus this Jacobi pseudo-inversion Jacobi thing, which is the kinematic null space. You can also take here the NC. So you could also take this NC from here if you do exactly the same. So it's the same submanifold, but with different normal vectors, but it will still be consistent with the constraints. Then one question was why NC would not be reduced to the zero matrix. So why this part here is not identity. So this null space is only then zero if all the constraints are, if the constraints are fully occupying my system. So if nothing can move anymore. So if all the constraint, all the forces like block the system dynamics, then it would be 0. And the first one was that we're using here again Q double dot instead of U dot. Apologize for this. I have a lazy way in how I'm writing this, and I told you this from the very beginning. This is probably like in all the literature that you find, people very often make this. So to do it very correct, I would have to write here U dot, and the same here with the Q double dot. So what I write Q double dot, but I mean U dot. All right, so that concludes this part. We applied this. I will spend like 10 more minutes to show you, to extend this a little more in the two examples that we looked at. So we looked at this simple card pendulum, where we said, okay, we have now this card pendulum, but we have a vertical motion which is blocked. So we have it sliding here on the ground with zero friction. So we can only produce force in normal direction. So this vertical motion was locked. We said vertical motion is locked. So that means we can't accelerate in y direction. So that must be 0. So we calculated this contact Jacobian for that blocking. And this contact Jacobian is the contact Jacobian that also goes here into the dynamics equations of motion with the corresponding contact force. So if I want to calculate now for a desired motion, what is my tau? I can't, because I have my force and my acceleration in here. That's why we had to project this first. We looked at kinematics. If you look at the kinematics, we have here the contact constraint, first equation, which means the actual Q double dot has to be consistent with that constraint. So it must have this coupling term, and then it must be this in this null space times a generic Q double dot. And if we do now, if you take this JC that we calculated here, and you would do the pseudo inversion times J and identity minus that part, you would leave with a 1, 0, 0, 1 matrix. What I told you last time is that the NC can be directly seen here, which is a 1 and a 0, because if I multiply that one with 1 and I add this one times 0, I get a 0. Now you see also the difference here. So this has only a second column vector, which is 0. So the span of this, so what the space that it spans is really only a one-dimensional system, although we have a two-dimensional matrix. So the rank of it is 1. That means we can, the constraint allows us to move in one single direction if we have that constraint active. So what we did then is that, okay, if I have this null space with this one instead of this quadratic one, I have a different dimensionality NC than in this NC. And if I look at this Q double dot here, and I look at this NC, I see this NC essentially just selects the first component, and the second one is 0. So this Q double dot 0 is a X double dot 0. So in other words, I can accelerate in X direction in an arbitrary fashion, and I'm still consistent with the contact constraint, which for this simple example is obviously visible. I can just take this card and the pendulum and move it in X direction, and I will not violate the constraint. But typically we cannot see this for a much more complex system, but for such a simple system, we can do it. We then looked at the dynamics, and we said, well, if I take my projector that I have here, I multiply NS, I get a 0. So this equation here has a 0 on the right-hand side. So I can take this equation here. I have to set the right-hand side to 0 because NC transpose times S transpose equals to 0. And I have the left-hand side. In this left-hand, we know that my Q double dot has to be consistent with the constraint. So it has to be that Q double dot. So I insert this Q double dot here. So I take this Q double dot, I insert it in here, which gives me this part. And now we know that, and that's again only because this example is so simple, we have the pendulum which is not allowed to move. So this system can only move like this. So the constraint that the velocity at that point must be 0 implies that my phi dot must be 0. So if I take this and I insert it in here, I will get this to be 0 and that this to be 0, plus we have NC times gravity part. So if I take this NC and multiply this G vector, I get 0 also. So this also cancels out. What is left in the end is this NC transposed MNC, which only selects this first component of the mass matrix. So that I end up with a reduced dynamics description, which only says the total mass of the cart and the pendulum times the acceleration in x direction must be 0. So what does that mean? If I'm blocking this system on the ground, all I can do is I can move it in this subspace in horizontal direction. So the x double dot times the acceleration here must be the external force in this direction. But we don't have an actuator right now. The only actuator is in this degree of freedom. So in other words, this is a free moving setup. One degree of freedom, total mass is given, the acceleration is what we have to identify depending on the initial conditions. And this torque does not change the motion, so it doesn't have an influence here. However, we know that there is, if I do now the inversion here of NS transposed, which is NS 0, so if I take this one, I invert it, I have a null space of it. And this null space allows me to change my torque such that I'm changing the external force, but I'm not changing the motion. Now, this was a very nice, simple example that allows us to do all of that analytically. And we ended up with an analytical description of a dynamics equations of motion in the subspace where the system can move. And we can also do this for determining the force. But this is not generally possible, but it shows you what is happening. We are taking a higher dimensional equation of motion, which is subject to external forces and actuation. We reduce dimensionality of these equations of motion to get rid of the external forces. In this case, we also got rid of the torque, not necessary. If I would have here an actuator, so assume that you would have here an actuator, which produces a force, we would see this here because that wouldn't be completely reduced. So we had a different S matrix then, and that wouldn't be completely removed. And you can do now the exact same thing also for the horizontal case. So if you have it here, I don't go through this, I leave it for you to look for it, but it's essentially the same thing. But already here, it's getting very tricky because the problem is the following. The null space for the vertical part now all of a sudden couples motion in x and in phi direction. So only a coupled motion of x and phi is consistent with the constraint. In fact, if I move left, I have to move up. So these two motions get coupled. So the reduced order dynamics must happen in this coupled subspace. So I get a q double dot 0, which is coupled through this null space projector in x and phi. And I have reduced order dynamics in this q dot 0. Okay, so there is one question. How can we ensure that NC we get as a null space of JC is the constraint consistent one? So what is important is always that NC transposed, I write this here, so NC transposed times JC transpose must be 0. So that is the requirement to be a null space projector matrix. How can I see directly the relationship between tau and force? Now, this is a tricky one. In here, what we can do is we can analyze, if you look at this thing here, we can split this JC. We get one subspace which is independent of force, one is independent, one is depending on force. So what you can do is you can solve for one and then insert it into the other one. You can always go back to this equation, which you had here. You can always go back to this equation here. This is always true. This means given your torque, you determine your force independent of the acceleration. So the torque determines the acceleration subject to the constraint and together the force. This is what you can see in this equation of motion. So I'm going to stop here for that part. If there's more questions, we have to go to Piazza. Maybe in the end we have a little more time because I need some time to go through the exercise that we had this week, the quiz that we had this week, which was related to a quadruped. For those who are interested, here are two, in my eyes, very nice publications about how to handle null spaces. Again, it's really not part of the exam, but if you want to do research about it, read these two papers. All right. So what we looked at in this exercise was the kinematics of a floating base system, which is this quadruped, 4 legs, 3 degrees of freedom each, and one is in swing. And we asked how many generalized coordinates that we have, base coordinates, and so on and so forth. So let's start with the first one. We have here generalized coordinates is 12 actuated ones, plus we have typically 6 for the base. Base coordinates are 6, 12 coordinates for the joint, and the contact constraints are 3 constraints per leg. We cannot move in X, nor in Y, nor in Z, and we have 3 legs, so we have 9 constraints that we have to satisfy somehow. Now that's a pure kinematic analysis of the whole setup. Then we had to write down the contact constraints, ask ourselves how many degrees of freedom remain adjustable and which degrees of freedom remain adjustable. To do this, what needs to happen is that we are looking at this R here. This is R, O, P, I in I. And we say that the velocity of that point must be 0 and the acceleration of that point must be 0. So we write it for the first leg, second leg, and third leg, both on velocity as well as on acceleration level. Quick recap here. So this is a matrix which has 3 entries in 3 rows, and on the column side we have then 12 plus 6 degrees of freedom. So we're constraining 3 position directions, and we have Q dimensionality of 18. That means we have 9 independent constraints, which leaves 6 independent base constraints. So we can completely move the base through these constraints. 3 are in the swing leg, and 3 are internal force directions. And we see this here also if you look at the illustration. So through these 3 legs here, I can move the position of the base and the orientation of the base, and I can calculate or determine an internal force. So 1 internal direction, 2 internal direction, 3 internal direction. So we have essentially 9 actuators that command 6 base coordinates and 3 internal forces. And then we have 3 additional degrees of freedom here to control the leg. Now, given a desired swing velocity, what is the generalized velocity? So we do just inverse differential kinematics, and then question if it's unique, and some question if it's possible to follow desired swing trajectory without moving the joint of leg 4. So let's start with the first one. We have these contact constraints given from before. Now we're introducing an additional task which says we want to move the swing velocity, the swing foot, along this predefined trajectory. So we have a 4th task which goes in here. So if I look at the stack of that, we have now a J which has 4 times 3, so equal to 12 constraints, but I have 18 in queues. So I still have a redundancy in here. So if I would put, just do inverse differential kinematics with that, I had infinite number of solutions. So that means also if we want to move a desired swing trajectory without moving the joints of leg 4, what I could do is, so assume that this is my 4th leg. What I can do is I can, instead of moving these joints along a predefined trajectory and not moving the base, I can move my base to move my whole setup along the predefined trajectory. And even if I want to keep my center of gravity or a point in my body fixed, I can still move the orientation of this body such that my end effector follows a predefined trajectory. So I have multiple ways I can make my end effector move without violating these constraints. The additional constraint, which says that these joints, I select the joints of the 4th leg. So I select these 3 joints out of my queue dots, and set these ones to be 0. I inject this as additional constraint in here, and then I do my inverse differential kinematics. So I have to also have a 0 here. And even then we have a redundant problem, because even if I look at this now, I have 5 times 3 equal to 15 row dimensions, and I have 18 columns. So the rank of this is 15-dimensional, but I could have 3 more degrees of freedom to be locked. And this is what is important once you're looking at this in a singular configuration. So imagine you want to move now your end effector while keeping your base orientation and position the same. So what's happening is the following. You're moving the foot along the predefined trajectory. Now, once you're reaching a kinematic limit, of course, that foot point is not tracking it anymore. Now, if I write everything into one task, and I have task 1, which is keeping the contact constraints and keeping and following the 4th leg trajectory, and we have the second task, which is keep your base position and orientation the same. Now, if you formulate everything as a single task, what I do is I stack J1 and J2, and I do the pseudo-inversion of that. Now here we have 6 times 18, and here we have 12 times 18. So this J here is 18 times 18 and has rank 18. So in other words, I can take the pseudo-inversion of it, and I don't have a null space to move. So what is happening here is if I'm reaching a singularity, so I cannot move my elbow, for example, anymore, I'm gonna start violating all the individual constraints equally. So I'm violating all these constraints somehow equally to make the system still follow. If I do it with multiple objectives, so hierarchically, I take the Q-dot to be consistent with the first task, and then I have to determine my Q.0 to fulfill the second task without violating the first task. So we have done this before several times. Then the difference is that the first one minimizes the whole objective, while the second one minimizes only the second objective, while satisfying for sure or ensuring the first one. So in other words, we ensure that we are consistent with the constraint, we are following the end effector, and we're just trying to somehow make sure that the base is barely moving. So what will happen there is if I hit my limit, I will still continue to follow my end effector, but I have to modify then my base. And this is something that we're using quite frequently in leggedrobotics to ensure that your system is able to track a desired motion, even in case of kinematic limits, if the environment is not as you expect, and so on and so forth. And I have an example in the case study that will come this week, where we discuss this in very detail. We have a walking machine going across uneven ground, and then you see like the system tries to keep the pose while moving. Once we hit the kinematic limit, we adapt the pose to ensure that we can still reach something. We also do this permanently. If we have to grab something somewhere and we can't reach it, we try to balance ourselves, violate other constraints that are not that important in order to be able to grasp something. All right, so there's one question. Wouldn't there be some? Yeah, so the last question here is a question whether there is no limit. So can the leg 4 move arbitrarily? And I think like what we discussed just now is exactly these problems, is exactly the solution for that problem. Even if you would not be able to further extend, so if all the legs become stretched at some point, you again need to make sure what is more important. What would be done typically is that you say, well, most important is that my contact constraints are still valid. So I will put this into priority 1, I will put this into priority 2, and I will put this into priority 3. And what you would also do typically is in here, for this, in particular for this third priority, because we have in here positions and orientations, you would add a weighting matrix. So instead of just fulfilling this part, you would weight the whole cost in order to make sure that you have a proper balancing of rotational offsets and positional offsets. So this concludes the leggedrobotics part. Next week, we're going to have the first case study. Now, what I would typically do is that I would bring the robots to the lab, and it would give you some introduction to what you're doing there, present the case study, and you would get a better feeling of what robotics research in this area is. Now, this we can't do this year. So what I thought to do for next week is the following. I will upload the case study as a pre-recorded video tonight. This is about 1.5 hours, like pure frontal lecture. But then we offer you next time during the live session, instead of a standard Q&A session that we do like this, that we have a virtual lab tour here with live demonstrations. So we're going to send out invitations for that, where you essentially join a spatial chat, so you can attend as if you were here. You see what's going on in the lab. You can then visit the live demonstration, so you see how things work and how things are failing. The researchers of our lab will be there and operate the robots, present that to you, and also ask questions, answer questions that you may have. Questions which are not necessarily related to the class itself, which is more related to the topic of legged robotics or other robots that we're going to present you. I think it's important that also in this time you get an opportunity to see what's going on in labs, how the lab life is, plus to have an opportunity to discuss with the researchers. It's important that you can also position and present yourself. So we'll also have the opportunity there that you will get a number of semester and master thesis proposals being presented. You can browse through that. You can chat with supervisors if you have questions or if something is more interesting for you. The whole thing starts at 10:15, not like this week at 11, and we're going to do it for 2 hours. I hope many of you are joining. It's the first time you're doing this, so it's a high risk thing. We don't know how and whether it's working out, but I hope that we have a successful demonstration session, that you get a little bit of a feeling of how it is to be at the lab. With this, we're closing here. I thank you all for the attention. I wish you the best for tomorrow's midterm, and then see many of you next week in the live demonstrations with the virtual lab tour. Thank you very much, and bye-bye.